Alright, the last, and that green took forever to get off the board. The last thing that I want to do in this, I just showed you a formal proof of validity using symbolic logic and showed the equivalence in the Polish notation system as a demonstration, as itself a proof that the systems are completely interchangeable. The last thing that I want to do is to show you a proof that I'd done in one of the videos of predicate logic in the series, some videos between 4 and 8, I forget which one it was. I'm going to use exactly the same problem. I might not solve it the same, I probably should solve it in the exact same way. And I'm going to show you how that problem translates to an equivalency and a formal proof for validity in predicate logic using the Polish notation system. I'll say that again because it's a mouthful, right? We're going to use, we're going to deduce and prove using a formal proof for validity, the validity of an argument in predicate logic, and show and demonstrate also how that argument is equivalent and equally deducible to a valid claim using the Polish notation system. Mouthful. Alright, so I wanted to get sort of not the most difficult type of problem, but a problem that would, have a lot of different aspects to it. Predicate logic problem, and here we go. So we have, my markers are killing me today. Let me just put this here so I'm not keep on using it. Okay, so one. Where are we? Okay, for all x, ax, then bx, to for some x, ax and dx. And the conclusion that we're trying to get to is for some x, bx and dx. Okay, I did this problem in a previous video. We're going to use exactly the same steps to solve the problem, and then we're going to show the equivalency of the problem. I'm going to move this out of the way. So C is conditional, A is disjunct, CAK is the conjunct, E is the biconditional, and N is the negation. And so I can get some room. So there's our system caking, gotta love it. Alright, first let's solve it, then we'll do the equivalencies. Alright, so number 3, remember always existentially instantiate before you universally instantiate. So we instantiate A, Y, and dy, and that's E, existential instantiation on 2. Number 4, universal instantiation gives us AY, then BY, that's 1, universal instantiation. And we're trying to get to this. Number 5 is simplification, so we get AY, and that's 3 simp. We use that to get the B. 6, if A then B, A therefore B, so we get BY, and that is, what is that, 4, 5, and P. And then we go to 7. What do we need? We need dx, hit the d's here, so we'll do a commutation. So it's dy ay on 3 8. We get dy that's 7 simp. Then we do conjunction on 9, so we get what? B. What do we need? by and dy. By and dy from 6 and 8. 6, 8 conjunction, then existential generalization, and we're done. where are we? What are we trying to do? Bx and d, whoopsie, dx, and that's 9 eg. Did I do that right? Yeah, I mean, I had to have done that right. Okay. Alright, so that's that. So we know that this is valid. We've proven, this is predicate, obviously, it's predicate logic. We've proven that it's valid in predicate logic. Now, let's do something a little bit more interesting. Let's try and do formal proof of validity for quantification rules using the Polish notation system. And let's see what happens. Alright, so we're here. So we'll just do equivalencies across the whole board. In the equivalencies, we will maintain our quantifiers. So our first quantifier stays on the outside. Then, same as before, we pull out the conditional, which is a C. Then we have our first claim, AX, and BX. No, I did that wrong. Well, no, I did that wrong. Sorry. AX and BX. BX. Okay. Yeah, if I would have made that a capital B, that would have been a huge error, right? Because there is no B in Kaken. So, this is exactly how you symbolize that, right? We recognize that we have a universal generalization. We recognize that we're saying that if there's a conjunction, and that conjunction connects the AX to the BX, right? There is an X that is an A, right? So if X is an A, then X is a B. That's what this says, right? So for all X to be formal, right, this would be read. And that's another thing too. I don't have the time to do it. If I went through and read all of this, it would just take forever. You read this exactly how you read this. It doesn't seem like you would, but you read it exactly the same way, right? For all X, if we know it's if because it's a conditional, right? If X is an A, then X is a B, right? It's read exactly the same way. So that's just like on the notation system. Line 2. So we have for some X, we pull out the. So we have this. We have this. Right? Pull this out. Conjunct is K. K. Ooh, I keep doing that. K. AX dx. Alright, so that's it. So then we have, where are we? That, so it's K AX dx. Alright, K AX dx. So that's that. And our conclusion that we're trying to arrive at, is this. Pull out the conjunct, K BX dx. That's what we're trying to arrive at. So given this and this, let's see what we can do. Now, we go here, AY and DY, and what would that be? Pull out the conjunct, K, conjunct is K, so pull that out, we have AY dy, that's 2EI, just like before, right? So what I've done is just so that this looks right, this and this is the generalization claim. We know that it's general. If I can write it, we know that it's general by. We know that it's general by the X. We see that we've instantiated just like before. Nothing has changed. We see that we've instantiated by the Y. Right. So we recognize that we're doing exactly the same thing. We've instantiated this claim. Okay. And I want to make it more level because it looks like it's like going down a bit. K-A-Y dy. Alright, so that's K-A-Y dy. That's 2. Existential instantiation. Existential instantiation always before universal instantiation. Rules still apply. Same thing applies. Nothing's changed. Pull out the conditional. Conditional is represented by C. C. Now we put in the AY. AY, BY, same thing. 1 UI. We see how that is. This is CAX. This is CAY. The difference being the x is changed into a y, the generalization is changed into an instantiation, b is exactly the same, the x changes to a y. Why does it change to a y? Because the generalization has been instantiated. I could have used any variable I wanted, for the most part, a through w, y in this case. So that's that, okay? 5 is just a y, right? And I'll write it like I've written it before, a y, and that's 3 s I M P. What is line 3? 3 is right here. AY, conjunct, right? And it's in the P place, right? We know that I can get simplification is P and Q. This is P, this is Q. Just like so conjunct, just so that you see this, right? It says if I have P and Q, then I can get P, right? So this is in the position of P. This is in the position of Q. This is the conjunct on the outside. P and Q. Simplification, I got the P, right? This has been translated here. It can't get any clearer than that. So that should be clear, right? That should be crystal clear. Okay. I'll erase that little nifty diagram there. Alright, so we have AY, BY here, BY, 4, 5, MP. Does it make sense? Let's look at 4. Here's 4, here's 5. If P, then, conditional, if P, then Q, P, therefore Q, right? If P, then Q, P, therefore Q. Same thing. Okay, so we got that. So we have this, dy and ay. Pull this out. This becomes k dy ay. Right, so we have k d, make it a smaller d, k dy ay. Same thing. The justification is 3 just as before. Hopefully, I hope this is, you're starting to get the hang of it, right? If you're not, then I'm sorry I failed. I hope I didn't fail. But you should start to see that you're getting the hang of this, right? I hope in going through this, you're getting the hang of this, to see that this is valid. This is completely valid, and it's an alternative method of solving now predicate logic, showing the validity of predicate logic, arguments in predicate logic, if I could talk tonight, and so on. Okay. dy, here we have dy, and that's 7 simp, 7, and obviously p, q, p, q, p, p, q, p, we know that that's right. Then we have by, dy, by joining this and this, right? Line, 6 and 9, I guess? Or 6 and 8. My lines are all crooked, but it's the same, 6 and 8, 6, 8, C, O, and J. Okay, and then, yeah, 8, 9, 10, that's right. So these two are combined, I get by dy. Then what do? I instantiate the claim, exactly as I would before, right? So then I get, there is an x such that we're going to conjoin the claim, right? Because remember, we need to conjoin the claim. And then what do? This has to change from the instantiated claim to the general claim. So it has to be bx now, right? Because what we've done is look, you can see it here, right? There is an x such that x is a b, such that x is a b, and, right, this is this, and x is a d. And you solve the problem. And just the last bit, it's 9 existential generalization, and that's it. So in this video, I was, it's just it's a different way of looking at the same problem. That's the only thing it is. I haven't really done anything novel here. All that I've done is I've proven that the systems are interchangeable, that the Polish notation system can be used not only to formally prove arguments in symbolic logic, but the Polish notation system can formally be used to prove arguments in predicate logic. And I've showed you both instances. We also saw that NAND NOR operators, the Polish notation system, symbolic formulations, and predicate formulations are all equivalent. The foundations are exactly the same. So all of this discussion of which one is harder or not harder, or more complex or not as complex, or more efficient or not efficient, it's all the same. It's proof that it's all the same. You've just seen it. What we need to recognize then is a further understanding of how all of this is integrated, how it's all one system, right? My goal, if I've done anything in this video, I hope that I've demonstrated that it's all one system. And my role in this, my role in this is just to, sort of get the discussion going, right? That's it. So go out and start discussing. With that, I appreciate your time. Thanks for watching this video. I'm Dr. Jason J. Campbell. Have a good day.